start by looking at this device that I have right here. This is a steam engine, and I've got a little fuel pellet down here that's burning, giving off heat, and heat is being transferred into this water. It's creating steam, and the steam is driving a little piston, and the piston is driving a little wheel. And so this is the device that's changing the thermal energy that goes into the water, into the kinetic energy of a rotating wheel. And this is an example of what's known as a heat engine. It's turning thermal energy into useful energy output. But something else happens here too. There's hot steam that comes out over here. I've got over here heat goes in, but out here heat goes out, and it's being exhausted into the environment. And why am I wasting this heat? Why am I dropping it into the environment, essentially? And it turns out the reason I do is because I have to. You can't do this transfer of thermal energy into kinetic energy with 100% efficiency. And that's something we'll talk about in the book. It's a consequence of the second law of thermodynamics. Now there's another device that we have here that will illustrate this principle of the heat engine. And this is a little device called a Peltier device. And the Peltier device runs between these two mugs. And this mug over here is full of cold water. And this mug I'll fill up with hot water. And we can tell it's hot because the temperature of the mug changes. And this is a color changing mug. So now I've got thermal energy here, and this is something we're going to call the hot reservoir. And over here I've got the cold reservoir. And heat is transferred from the hot to the cold, as you know, but as it does that, it goes through this little device. And there's a device in here called a Peltier device, and as heat is transferred through it, it takes a certain amount of the energy and converts it into electrical energy that we use to run a fan. And there we go. And so energy is being transferred from the hot reservoir to the cold reservoir, but a certain amount of it is coming off and being turned into useful work. It's spinning this wheel. This is a heat engine. Heat goes from the hot side to the cold side, and we extract some of it to do useful work, in this case, running a fan. This is an example of a heat engine. And I have another heat engine right here that can run off a much smaller temperature difference. And this one can run off the temperature difference between a cup of hot water and the air in the room. But there still has to be a hot reservoir where the heat comes in and a cold reservoir where the heat goes out. You can't convert thermal energy into other forms of energy with 100% efficiency. That's a consequence of the second law of thermodynamics. Let's think about the definition of efficiency from earlier in the chapter. Efficiency is what you get divided by what you had to pay. Now, let's look at a diagram of a heat engine. You can see that heat flows from the hot reservoir to the cold reservoir, but some of it is peeled off and used to do useful work. Now, think about this. How would we define the efficiency of the heat engine? We'll give you some choices. Okay, now let's focus on two elements. First, the heat energy from the hot reservoir, and then, second, the work out. The efficiency is what you get divided by what you had to pay. What you had to pay is the heat from the hot reservoir. That came from burning fuel or some other heat source. What you get is the useful work output. So, therefore, the efficiency, what you get divided by what you had to pay, is the work out divided by the heat in. You can have heat engines that will run on very, very tiny temperature differences. You can have heat engines that are more or less efficient, but there's a theoretical maximum to their efficiency. And that is a limitation of nature. Now, if you take a heat engine and you run it backwards, if I take this and don't let it spin this way, but I make it spin this way, it turns into what's called a heat pump. It actually takes heat from this side and pumps it into the bottom. It pumps it into the bottom. And the little devices that I had over here will do that. They will work as a heat, not as a heat engine, but as a heat pump. They will move heat from one side to the other in the opposite direction from how it would naturally go. Normally, heat would go from here to the room. But if I take this and I spin it the other way, I can make it go from the room into the cup. That's an example of a heat pump. And you have at least one heat pump in your house, your refrigerator. And the refrigerator doesn't make cold. What it does is it takes heat from the inside and pumps it outside. So if we take a look inside this refrigerator, the inside of the refrigerator, as revealed by the thermal camera, is quite cold. And I'm going to take a picture relative to my hand. Warm hand, cold fridge. But we haven't just like destroyed that heat. We've dumped it someplace. And so as a consequence, there has to be someplace that's warm. And what's warm is the back of the refrigerator. And it's taken heat from the inside and dumped it into the outside. It's dumped it into the room. And so it's just moved it from one place to another. It conserves energy. And it also satisfies the second law of thermodynamics. Heat would naturally go from the warm room into the cold fridge. We're forcing it to go in the opposite direction. And to do that requires an energy input. So the next thing we want to look at is how matter changes with heat and with temperature. And that's something we'll look at in Chapter 12.